So as you see there, my name is Pablo Ribalta. I'm senior engineer in future processing, and today I will be talking to you about deep learning and what happens when we build machines that can learn. But first of all, let me show you something.
Okay, that's a cat sitting in a bed. The boy is petting the elephant. Those are people that are going on an airplane.
Okay, so this is a 3-year-old child describing what she sees in a series of pictures. She may still have to learn a lot about the world, but she is already an expert at one very important task, which is to make sense of what she sees. We live in a very advanced era where we can send people to the moon. We have smartphones that talk to us. We even have radio stations that play only the music that we like. Yet our most powerful computers still struggle at tasks like this. So today I will be giving you a progress report in deep learning, which has become one of the most frontier and challenging topics in modern computer science. So let's start by talking about how to teach a machine to do something that we know how to do. Typically, we would just write a program for it. We would just specify all the steps between the initial state and the goal state. And those who have some experience with this will know that this requires of an excruciating level of detail. This is a very difficult and error-prone process. However, how to teach a machine to do something that we don't know how to do? Now that is a different story. This was the challenge of this man. He's called Arthur Samuels, who in 1957 wanted to teach that computer to be able to beat him at the game of checkers. So for this, he had this idea. If he could compute a play against itself thousands and thousands of times, maybe he could eventually learn or teach this computer how to play the game of checkers. And indeed, it worked. It worked so well that only 5 years later, this computer was able to beat the state champion of Connecticut. But those were the humble beginnings. Let's fast forward almost 60 years till nowadays. We have Google. Google was perhaps one of the first commercial successes of machine learning. They proved that it's possible to display information, to retrieve data, only by how the data that is stored is connected between itself. So this means that this algorithm was not specifically programmed to do what it does. It learns from the data that it stores, and it adapts. This is indeed machine learning. From then, many commercial applications of machine learning have appeared. For example, Netflix or Amazon, they suggest you movies or books that you may like to buy or you may like to watch or to read. It can even be unsettling because you have like sites like LinkedIn or Facebook that may know who your friends are without you knowing how they do that. So this is also machine learning. However, as a byproduct of all this sudden interest in the machine learning field has appeared a new technology, which is deep learning. So let's see how, for example, a deep neural network would work. In this case, trying to figure out who is the person in this image. Deep neural networks are biologically inspired systems that, of course, inspire themselves in our bodies. So here, for example, the bottom layers try to map small regions of the image, similar to how the cells in the retina would do. They don't focus on the whole image field. They just take a tiny portion. Then they activate. And after their activation, what we get is a series of features that are just random. You can see here edges, you can see gradients, you can see a lot of stuff, but not much of it makes sense. As we travel deeper, these features aggregate. They aggregate, and we start getting more semantically charged features. We can see here an eye, an eyebrow, a mouth, maybe a nose. So we see that this is starting to resemble something. We continue going deeper, and all these facial features combine into faces. We see full faces here. At this point, these bottom layers have performed an unsupervised feature extraction. We don't need an expert to select what features are important. The network itself is choosing what matters in this case. In the bottom layers, we perform simple linear classification, and we can see that this person's name is Albert. As you see, this is very simple. This is very similar to how vision works in humans. These systems are inspired in the design of human brains. So it means that they don't have any theoretical limitation of what they can do or they can achieve. The more data that you give them and the more computation that you give them, they just simply, the better they get. So what is this change of machine learning to deep learning? Is some new buzzword or something like that? So it's actually not that different. It used to be before that we could not get very deep with our neural networks, basically because the hardware was not yet there. And we hadn't quite yet figured out the mathematics behind the functions that drive the learning process. This meant that we were very constrained and limited into how deep and how complex our networks could get. But some things changed. In the 90s, there were major breakthroughs in the functions that regulate learning. For example, stochastic gradient descent happened. And now GPUs are widely available for everybody for these kind of computations, not only for rendering graphics. This has the result that the amount of features that we can extract just explodes. We don't have to think only about the neurons that we have. Here what we see is that we process data in 3 dimensions. We take slices with a lot of features, so the dimensionality of our problems just grows. The amount of features that we can extract just simply explodes. But you can say, oh, this must be super complicated. Of course. So it's not that difficult. In this particular case, convolutional neural networks are based on 2 very simple operations. Those that have some background in image processing or computer vision may be familiar with this. But the 2 main operations are convolution and pooling. What is a convolution? When we are performing a convolution, we have what it's called there on the right in green, a convolutional kernel. Convolutional kernel can have different layouts. Once we apply a convolutional kernel to a signal, be it an image, be it sound, be it a time series, we modify the fundamental properties of this signal, highlighting some particular attributes. So for example, we have convolutional kernels that are very good at extracting horizontal edges or vertical edges or giving us gradients. So each layer performs many of these operations. So whenever each node activates, is applying many convolutional kernels on a subregion of the image. This acts as a sliding window, as we see here. And what we have at the end is a convolved feature. So we have, well, here we have our image, which is basically a matrix of numbers. And at the end, we have a compressed image that has highlighted the attributes that the convolutional kernel was looking for. This happens, as I said, many times in each neuron. So we have here a 5x5 image, and if we apply, for example, 4 or 5 convolutional kernels, we can end up with a 15x15 aggregated composed feature. So we see how dimensionality just simply explodes in this case. From one image that doesn't tell us anything, we end up with many convolved features that reveal hidden patterns in this portion of image. Okay, so at the end, what we want to have is one label. So how do we go from that many dimensions into something smaller? So for this, we use pooling. In this case, max pooling layers. Pooling simply means to downsample. We go from very, very big chunks of data to some smaller representative chunk of data. So in this case, max pooling works splitting a convolved feature or a slice in different parts and just getting the highest value from each one of them. So for example, the highest from this red part is the 6, so we put it here. Here is the 3, and you can follow the rest. You can say, oh, but we are losing information. We are just dumping the rest of information. In this case, we are dumping the 75% of the information. How that can be good? So this research has shown that this has positive effects. In a sense, that we only keep the highest activations, which means that we only care about what affected what caught the attention the biggest to our network. And removing the extra information, we prevent a very common problem in machine learning, which is overfitting, which means that our network becomes too used to the training data, and then when it performs in the wild, we are not able to achieve the same results. So we see that these two very simple operations applied millions of times can give us very powerful artifacts for learning. But how much can these networks learn? So we will see now that indeed these networks can learn and can learn beyond human abilities. It's hard to believe. But one of the best examples of this was the Merck drug research contest. It was organized in this data science portal Kaggle. This was a competition where Merck proposed a framework, gave some data sets of different molecules and what effect they have in the human body, like positive and negative effects. And the idea was to develop the next generation of medicines. So the most amazing thing is not that a deep learning solution won this. In this case, made by the University of Toronto and Geoffrey Hinton, who is a very important person in the deep learning world. The most amazing thing is that they did it without having anyone in the team knowing about chemistry, life sciences, biology, or anything of this kind. And they did it in 2 weeks. This was so remarkable that it was covered in the cover of the New York Times. This was just an incredible achievement. But it doesn't end only there. Because computers can learn, they can only see, and they can even see better than humans. Let me talk to you about the ImageNet challenge. ImageNet is a data set that slowly has become like an event attached to it. It has become like the Olympic Games of computer vision. In this data set, we have a lot of images that are labeled, and the goal is to find what is in each one of these images. We have like tens of millions of images. So here we would get this picture, we would try to extract what objects are in this picture, and then we try to identify to what class they belong. So 2012 was a great year for deep learning. It was the first time that a deep neural network participated in the ImageNet challenge, and it just simply pulverized the existent solutions. This is what we see here, classic machine learning. These algorithms were developed and fine-tuned during decades. And a very small convolutional neural network that nowadays is obsolete just simply cut it almost into the half. After that, every year, a deep neural network has won this competition, and we are at a 3.08% of error rate, which means that we have already surpassed human abilities at image recognition by these systems. But they cannot only see, machines can understand. What do I mean by understand? This is from a paper where we have a deep neural network. We are feeding it some images, and he generates some annotations from these images. This neural network has seen a man, has seen a guitar, has seen a black shirt, before, but it has never seen this picture before. Any one of the rest, for that matter. However, it's able to understand what is in the picture, and it can give us a summary. However, it doesn't end only there, because this has some problems with context. But here we have what I consider an amazing display of learning. What we see here is a neural network that is able to learn the style of a painting. And then once we supply a picture, it is able to transfer the style, the brush strokes, the colors, how the edges are painted. And the result is just simply amazing. This would take years for an expert, years of developing knowledge and skill about this, and this network can just be trained in a couple of hours. But what do we get when we put all these things together? Yeah? I'm sure you all know about this IBM Watson. For those that don't know, IBM Watson is this big neural network from IBM that has been recently switched to deep learning. And here you can see it competing in this Jeopardy American program against the world champions that defeated them. So Watson has turned its eyes into medicine recently. In an article by, I think, a couple of months ago, they tried to compare diagnostics from Watson related to lung cancer. They tried to compare them with the treatments proposed by an expert. And not only they found out that Watson was as good as the expert when he proposed these kind of treatments, it also proposed more alternative treatments. And some of these alternative treatments, the doctor didn't even know about their existence. This is because in medical research, there are around 160,000 articles published per year. 160,000 per year. Even if you are the most brilliant doctor, the smartest person in the planet, there is no possibility that you can catch up with such amount of information. But for a deep learning system, it's perfectly possible. Some applications of deep learning for lung cancer have shown that when we analyze images of tissue from a microscope, these systems can identify features that have a correlation with the prediction of survival for each patient. The most amazing part of this is not that it works, which is also amazing in itself. It's just that it also generates insightful science. What do I mean by that? I mean that this system found 25 new features related with survival rates that were unknown to the medical community. Some of them were even taught wrongly in medical schools for decades. And this system just found out 25. So what do we do in deep learning, in feature processing? What is our relationship with it? So this is Econib, the project where I'm involved, and we are trying to use deep learning to help radiologists to identify tumors in lungs of patients. We aim to provide a platform for physicians to collaborate and to improve their skills when trying to diagnose cancer. TexRat is the tool we develop, is already being applied in several hospitals around the world, and it has a big component of machine learning inside, and we are trying to introduce these new deep learning methodologies. How does this work? So a way that we can find out about the tumors is we have a series of computerized tomography images. This is what CT stands for. And we also have a series of PET images, which are positron emission tomography images. And we build a deep neural network for this, and we try to classify each pixel that we see in it. The process is simple. We try to find the lungs, and then here we get more introspective information. This allows us to display to the physician some information. Here you cannot see it very well, but well, here we have a highlight contour of the lungs. We have here a potential area of interest. Here is the internal walls of the lungs. And here the contrast is not very good, but you can see it in the slide that here we have a heat map that tells us that, hey, there is a hotspot here. You have to try to figure out what's going on here. We really believe that neural networks can make a difference in this, and they are being widely applied in medical industry. So all this is really cool stuff, but okay, you would like to try it, you are technical people. You would like to introduce it in your job, you would like to start doing research about it. So here there are some alternatives for you. If you are a Java guy, you have Deep Learning 4J. If you are a C++ guy, you have Microsoft CNTK and Caffe. And for Python, you have Keras, Theano, and TensorFlow. We will see what it is. The cool thing about this, I cannot talk about this because I have never used it. In Econi, mainly we use this ecosystem. We use Python for prototyping. We use C++ for deployment. This runs as a C++ code, but it also gets compiled as CUDA code by the framework itself. So we are also using GPUs. The same happens with Python code. We say, oh man, Python is super slow. It might take hours or days to compile one of these things or to train it. Well, if you write this kind of Python with Keras, this Python code gets compiled into GPU code. This is how to build a convolutional neural network in Keras in 25 lines. I wanted to show this because all this topic might seem very complicated, and it's true that it's not trivial. But a lot of frameworks exist that make all this process very simple. And these frameworks are really, really powerful. The way that it works is that we just have to import the layers we want to use, the model. So the model is where the little layers live, let's say. And we can even import data sets. So the way we would use it would be that we load a data set, in this case MNIST, which is a widely used benchmark data set with digits. And we can create a model, empty model, and we add here the layers that we want to use. These numbers, the first one is the number of convolutional kernels we want to have in each layer. Here is the size of each one of these kernels. Here is the activation function that we will use, but you may need to learn a bit more about that, but it's not really that important. And here we have the input shape. We don't have to worry about the dimensions as we get deeper into the network because we only have to set the input shape. Here what we say is that we will process one image at a time, and each image is 28 by 28. Max pooling, we've seen what is max pooling, 2 by 2 max pooling, the same example as I showed you, another convolutional layer, another max pooling layer, then we make it flat, and we show 100 nodes at the other end. So we go from having a 28 by 28 image to a 100-sized feature vector. What we do here is that we compile this model. Here this code is being compiled into native CUDA code, so this will not be Python anymore. The program will take a little bit to run, maybe like 10, 15 seconds, where it will seem idle, but it's compiling all this Python code into CUDA code that then will run as C++, GPU-friendly code. And here what we do is we feed it. Well, here it says classification, but it should be training, classification. It would be with model predict, but we are taking training data, training labels, running it for 50 times in a loop with 128 samples at a time, and we validate it with what we have extracted here, training set, validation set. So, well, this would actually perform classification. So you see, 25 lines of code to run a deep learning neural network. Really, really doesn't get easier anywhere. So I hope that you want to try it, that you will try to read about it, or that at least it has helped you to understand how these mysterious systems work. I would like to thank you, all of you, for your attention. And if you have any doubts about how these systems work, we have time for questions now, but you can grab me in the corridors. So thank you very much.